it's not like a training. It's not like a training program. So this is to throw some light on what we have experienced over the period of 2, 3 decades in the area of energy audits. So as you all know, how energy audit started was way back in the 70s when there was this first oil crisis in 1973. The oil prices went up by 4 times, and many of the economies had to suffer because of that. So that is when the country started thinking about the efficient use of energy. So prior to that, we had boilers which had flue gas temperatures of about 600 degrees centigrade, and no problem because the energy was very cheap. So nobody really had a concern about how efficiently we were using the energy. But thanks to the oil crisis, it was an opportunity for us to rethink on how the energy is being utilized, and how we can optimize the energy, how we can reduce energy consumption. So these were the things that brought about by the oil shock. And today, over a period of nearly 5 decades, we have seen a dramatic improvement in the way in which we use energy. So plenty of energy saving measures, ideas, technologies, innovations have taken place. And today we are in a position where we can say that reasonably we have reduced our consumption maybe about 20 to 30% compared to what it used to be in the 70s. So this has been made possible by variety of cross-section of the people from the industry, especially because they are the ones who are using the energy ultimately in, in a large extent. And then thanks to the government which supported this energy efficiency movement in India, so plenty of awareness has taken place, plenty of sponsored projects, the government gave subsidies. So as a result, we have seen a lot of changes that have taken place in which the energy audits have been conducted over the period of 5 decades. So in the 70s, when these energy audits started, there were hardly any instruments, leave alone portable instruments. Even online instruments were not available to an extent what an energy auditor would have required. As a result, there were many guesses, assumptions, and still some amount of energy was being saved. But today, you compare that situation where people used to use a handheld pyrite, a chemical analysis or an offset apparatus for measuring the flue gas constituents. And it used to be a hard task. So you go up the chimney and then put the pyrite probe into the stack. Then with a bellow type pump, you pull in the flue gas and see what is the carbon dioxide percentage. And based on that, you suggest, okay, this is the excess air that you're using, and probably you can reduce the excess. And that was a scope. There was a scope for reducing excess air, and that time, 5 decades back, reduction excess air in the boiler used to be a major energy saving measure because there was very little awareness on how excess air impacts on the energy consumption. And subsequent today, you see 5 decades later, almost all the major industries have an online oxygen analyzer. They all realize the importance of excess air. And not only the oxygen analyzer, it is hooked up to the ID fan, FD fan. So you have a optimum excess air being used throughout the day cycle. So in fact, the SCADA, DCS, all these have made things much simpler for the energy auditor. We need not run around much in the field. So the data acquisition has become very, very simple. And we can also see the trend over the past 2 months or 6 months, what has been the trend of various parameters. So the modern day instrumentation has given that luxury. So now this is a situation, we have a lot of data that is available, and what do we do with the data? Can data alone save energy? That is the question here. So how do we go ahead, having come to a stage where all data is available, and from here, what will be the kind of activities that need to be performed maybe over the next decade? Let us say, as we say, energy audit. Today, all the industries are quite aware what an energy audit means and what is expected of an energy auditor. So they're quite aware and they have become very demanding, in fact. So the energy auditors level has to raise consistently because more and more people are getting educated, getting aware, and these exams from the Bureau of Energy Efficiency helped in large measure in upgrading the skills and knowledge of the people working in the industry. So the energy auditor is a tough job. It's no longer excess air reduction or compressed air leakages that is going to be convincing for the industry. So the industry expects something beyond, something more, tangible energy savings, tangible reduction in the energy bill. So the energy auditor has to raise his level several times above what is at present, and also meet the expectations of the industry personnel. So as we know, every industry has an energy manager, the designated consumer at least. So the designated consumer has also gone through this examination system, and they're quite aware of the knowledge and about the subjects and what is expected of an energy auditor. So more and more demanding consumers are expected in the near future. So how do we gear up for this? And the conventional energy audits, which is dominated by measurements. So the last maybe about 5-10 years back, if you see, there were a lot of portable instruments, power analyzer, ultrasonic flow meters, anemometer, all these instruments the energy auditor had in his bag, and so this was sufficient to impress the industry. When you go to industry and tell them you have all these portable instruments which can do magic, there were people who could buy this kind of argument. But today, it's no longer the case. Instruments and measurements and data alone are not sufficient. So at the end of the day, what is the percentage reduction in energy consumption? So that is what matters. So let us have a look at how possibly we could diversify from what is the convention to areas other than what we have been focusing on. So can we dive deeper into this process called energy audit? Can we extend the scope of the energy audit to go deeper into the process and see the ultimate area of energy utilization? So basically, we're talking about the end use energy use. Now, the importance of energy conservation is all very well known, and even the school kids are able to tell us why energy saving is important. Much awareness has gone in, and as we all know that what the fossil fuels are consumed by the world is about 95% of the total energy consumption. So 95% is supplied by the fossil fuels. How much we talk of solar, wind, and the renewables, and even including hydel, they all contribute to just 5% of the world's energy requirement. And fossil fuels not last long, as we know, and then we have already consumed 60% of all the resources. And the key is it is not going to exist for future generations. So this is something which has been drilled into the minds of the people over several decades of awareness building, and everybody is aware of this. So maybe in a few hundreds of less than 200 years, all these energy sources, fossil fuels, coal, oil, and natural gas will all vanish from this earth. And the question is, what next? So before that, this is an interesting slide on a work from the US uh, government. They commissioned a study to analyze how the energy is getting utilized in the economy. So if you look at the input to the US economy, 84% of the energy input to the US economy is from the fossil fuels. 7% is from nuclear, and 5% is from hydel, geothermal, solar, and all that. 4% is biomass. So this is the input to the US economy. And what about where it is used and the outputs? If you see, the useful energy is only 9%. That is the energy that is actually required to do some work. So if you see, that energy is 9%. That means the energy efficiency of the US economy is only 9%. Then what happens to the remaining 91? So here 7% is going for, of course, this can be considered useful for the processing of petrochemicals, for producing petrochemicals like plastics. But this 41% is what is called the unavoidable energy waste. So unavoidable is something thermodynamic limitation which prevents the complete utilization of the energy. So we have a boiler. A boiler will have a chimney, and out of the chimney comes the hot exhaust gases. So we can't close the chimney and say we are saving energy. Some amount of loss will take place. Or in an engine. So what happens to the engine? So there is going to be an exhaust, and exhaust is going to carry away a lot of flue gases, heat. So that is also unavoidable. Thermodynamically, as we know, the second law of thermodynamics, if you convert energy from one form to another, it has to be accompanied by a loss of energy. We can't have a 100% energy conversion. But 43% is what we call as unnecessary energy waste. This unnecessary is something which we can avoid. The simplest example is a temperature setting for the air conditioner. So if you're setting at 22 and you're using the air conditioner, and in case you feel comfortable at 26, you straight away save about 15% of the energy. So this is a waste. When you feel comfortable at 26, why should we go down to 22 and put a blanket over you? And also the air conditioner is on, the doors are open or the windows are open, they're not tight. Again, it's a waste of energy. So this unnecessary energy waste contributes to 43%. This is the potential for energy savings. 41% we will not be able to save. It will happen. But 43% is something which we can recover and save. So the same thing will apply for any other country. The input ratio may change between the type of energy sources, but the output more or less will be the same. Coming down to the local level, how the electricity flows. So if we have this 100 units of energy going into a thermal power station, form of coal, as we know, the efficiency of a thermal power plant is just 30%. So only 30% comes out as electrical energy. The remaining 70% is lost in the power plant itself. So out of this 70%, maybe about 50% will be going as heat loss in the condensers of the power plant. That is again inevitable. It is unavoidable energy loss. So the 70% will be the loss, whichever be the country, whether it is developed country or developing country, doesn't make a difference. So 30% electricity comes out, then it travels through the wires. You have this T&D losses is 9%. And then it comes to your transformer in your factory, quite efficient. 99% is the efficiency of the transformer. Then the motor, the efficiency of the motor is 90%. So you lose about 10% in the motor. If there is a pulley or a chain or a belt, 2%, up to 2% loss will be there. Then it drives a pump. Efficiency of the pump, 75%. So 25% loss in the pump. Then you find the water is too much, you slightly close the valve. 33% is the loss that you would incur by closure of the valve. And then the friction losses in pipe, 20%. So finally, when the water goes into the overhead tank, the energy available in water is only 9.5 units. So of the 100 units that you have given as input to the power plant, ultimately what is available in the overhead tank is 9.5 units. And that is not all. Again, it depends on how you actually use the water from the overhead tank. You open the tap in the wash basin and you forgot to close it, the entire 100 units is drained. So now if you look at it, the potential for energy savings, the power plant is a peak of the efficiency. Nothing much can be done, though technologically supercritical power plants have been able to raise this bar, but only marginally. There's no dramatic improvement in the efficiency. T&D losses, technically, this is 9% is the limit, and that is also achieved. And here you have the motor, 90% is fairly good for an efficient motor. So up to this point, transformer, of course, included 99%. All these are efficient. But here, if you see, so much of losses are happening. That means ultimately the user end, as you go towards the user, the potential for energy savings appears to be quite high. We normally tend to stop with the utility. Maybe we'll go to the motor, we'll go to the pump, we'll measure the efficiency of the pump. So, and beyond that, what happens, how the water is used, where water is used, how much water is used, why water is used. So these questions are the ones which probably will take dominance in the next few years as we go deeper and deeper into energy audit. If you look at the definition of the energy audit as per the Energy Conservation Act, what does it say? The verification, monitoring, analysis of the use of energy. So the verification, what does this term mean? It can be very vague, meaning different to different people. So the verification of what? What are you having to verify? This is the data, and then the monitoring of the data, which is anyway being done by the industry, and then analysis of use of energy. So to what level this analysis has to be done? If there is a compressor, where do we stop the analysis? So we measure the electrical power input to the compressors as an energy audit. Diligently, we measure the power. We put the power analyzer. So we measure the power, and then today it's becoming a fashion to do the FAD test. I am not really sure how helpful it is, but FAD test is being conducted in all the audits, also demanded by some of the clients. And the leak test, of course, is also carried out. So is that all that is to be required of a compressor system audit? So as it stands today, we have more or less stopped at this point. So an air analysis, a compressor audit means FAD, leak test, and probably we suggest pressure reduction, all that. But If you go to the end use, where compressed air is used, what for the compressed air is used, is there an alternative way of doing the thing rather than using pneumatically? For example, in industry, we saw about 10 compressors being used. 10 compressors with pipelines of more than 2 kilometers running all over towards a place, and then not a very heavy job, it's a light turning activity. Uh, the screws have to be inserted into some of the coaches. So the torque requirement was very less, and air was being used, and leakages was up to 35%. So then we go into we saw this leakages, we saw this compressors have VFDs, they have some of them have soft starters. So every possible thing that can be done in a compressor has been done. Then you go to the air side, distribution side. Of course, there is a leakage, accepted. But beyond that, what can be done? As you analyze, we find that many of these operations which they were carrying out with pneumatic compressed air can very easily be done by uh, a battery operated a torque wrench or a drill, as a result of which about 8 compressors were eliminated. So they went in for this uh, the battery operated equipment, and which helped them to do away with 8 compressors. So final point, where exactly the use is taking place for the energy, that the definition of the audit doesn't tell you. It says analysis of use of energy, whether it is only up to the compressor, up to the pipelines. So this is something which we need to extend towards the process end use, and that is where a huge potential for energy saving lies. So ideally, when we look at an energy audit definition, we are looking at what type of energies are used in the plant, fuels, whether it's coal, oil, electricity, diesel, and how much energy is used. Typical audit questions would be like this. So you collect about 12 months data on various energy uses and where all it is used. How much does it cost? The cost of energy, the tariff for the electricity, cost of fuels, and where all it is used. This is the important question. So energy as it is received, maybe some of the fuel convert to steam secondary sources and then used in different places. So we need to make a schematic and say where it is used, and how much is being used is also a question that needs to be addressed. So how much energy is used and how efficiently it is used, which means you need to compare it with some theoretical or the design data. So whether the energy that we use is being efficiently used or not, and if not, how it can be managed more efficiently and effectively. So these are the typical, the what, how, and whys, the various questions we ask in the energy audit, and so this typically defines what energy audit is. More precise to the point compared to the definition as is given in the Act. Now, to what extent, what should be the boundary? That needs to be debated and discussed. So, if we go beyond the facility system, if we enter into the process, if we do this questioning to the process. So, these are the things that we need to delve as we move along from now on to make energy audits more purposeful. The other important question is many times, when we say energy audit, immediately the electrical engineer is held responsible. for the energy audit, conduct of energy audit, or if somebody wants to be an energy manager, energy auditor, the axe falls on the electrical engineer. So energy is not electrical. How it is or who is responsible for saving electrical energy? Now we have this the supply coming from the grid. This is a typical electrical single line diagram of the system, industrial electrical system. So we have the power coming from the grid. We have a transformer. So this is the first loss that happens in industry. The transformer, about 1 or 1.5% will be the loss. So transformer efficiency is pretty high. Then the after voltage reduction, the power flows through the cables. The second loss, what is the loss in the cables? Very minimum. It can be less than 1% for a typical industry. So you can't even quantify it. So it goes through these wires and then there is some loss, insignificant. Then it comes to the motor. So what is the efficiency of the motor? Say 90% is the efficiency, so 10% is lost. So your transformer is efficient, the cables are efficient, the motors are efficient by default. And at any load, irrespective of the load, these equipments are quite efficient. So where the electrical engineer is going to save energy? So it is up to the motor, the electrical engineer's domain. So how the electrical engineer is going to save energy in the transformer where it is already 99% efficient? He may save about 0.2%, but that will be insignificant compared to the energy consumption of the plant. Then the cables, what can you do about it? Maybe you can improve the power factor and see that the cable losses are reduced, but the loss itself is insignificant, and further bringing down the losses will not be detected by the meters. So much is the potential in the cables. Then the motor. Okay, we talk of IE3 and all that, but no one wants to disturb the existing motor just for probably a little bit of savings, which you're not even sure of. So, as you can see in many of the industries as you go for audits, not many people buy this argument that you have to convert to IE3. A motor, which if you're buying a new motor, yes, it makes sense, but in a motor which is already in operation, so it doesn't make sense to convert to IE3 in most of the cases. So very rarely you'll find a replacement of the existing motor with IE3 quite economical, where it is 24-hour operation and highly underloaded, so or reworn many times. Then there can be a case, but still it is very difficult to prove in the field that there has been a tangible gain by going into IE3 mode. So that means very little option is there in the motor itself, transformer, cable. So how electrical engineer is going to save electrical energy? So that brings us to the question, which equipment consumes energy? Is it the motor? So motor itself does not need any energy. There is a driven equipment, a compressor or a pump or a blower. So the energy is demanded by the compressor. The motor simply supplies whatever demanded by the compressor. The energy demanded by the compressor is supplied by the motor. So the motor is only a broker. It takes electrical energy, converts it to mechanical energy. The actual consumption is by the driven equipment. Not even by the, not only by the driven equipment, but also this compressed air, where it is going, who is using it. That ultimate user, the production man, decides how much will be the energy demanded from the compressor. Quantity of air, the pressure at which he is using, will decide the power required for the compressor. That in turn will decide the power drawn from the motor or the power supplied by the motor. So when you want to save electrical energy, if you are arresting leakage, it is not electrical engineer's job to arrest the leakage. But the maintenance person, when he arrests the leakage, there is a reduction in electrical energy. And a process man is confident of using compressor at a lower pressure, then electrical energy is saved. It is not the electrical engineer who is saving the electrical energy. So as you can see, the potential for energy saving lies beyond this line. The electrical engineer himself has very little role to play in electrical energy savings. So this we will see by some of the case studies. Of course, many of the things are already documented also. And typically when you look at kWh, this is the energy that is required. We say it is the power into number of hours, the kilowatt. So when you want to reduce the kilowatt hours, we reduce the power required, we reduce the number or reduce the number of hours required, or both. Simplest example, let us take the example of lighting system. So when you replace a typical lamp with an LED, the power reduces. And instead of keeping it on for 12 hours, we reduce the number of operating hours to 10, then we save energy. So kilowatt reduction can save energy, number of hours of operation can save energy, and both of course can save energy. So in many of the applications, you will find this power reduction is possible, and in some cases the number of hours reduction also is possible. So this is as we were discussing the electric motor. So the general tendency is that the audit becomes highly electrical energy biased. So we were overseeing an energy audit, and we saw two energy auditors coming from the airport straight to the plant. They carried two big suitcases. So straight away they went to the control panel. They asked them to open out the panels and started putting the tongs into the cables without even knowing what the industry is manufacturing, without even knowing where the energy is getting used. So the concept or the perspective that we have here is that it is an electrical engineer's job, and it's all about electricity, current, amps, voltage, and power, and maybe KVR, the power capacitors. So the energy audit is restricted to this in many of the cases. But as we have seen, it's nothing great about the motor. In the audit itself, the motor has very little relevance, except for the fact that we may be noting the nameplate, how much is the rated kilowatt of the motor, how much power it is drawing. Beyond that, we are not going to disturb the motor at all. Also, because of this fact that electric motor, if you see the efficiency, unlike a pump or blower, you will see that efficiency remains same from 50 to 100% load. So even if you oversize a motor, no problem. There is nothing that you are going to lose. So the efficiency is kept intact. A motor operating at 50% load has the same efficiency as a motor operating at 100% load, and also in between. So which means we don't lose much by operating a motor at a lower load. So this used to be, there were times when people were giving reports which said that we have replaced 30 HP motor by 20 HP motor. So there's a 10 HP saving, and huge savings was projected. So this all happened, in the initial stage of energy audit when we were all learning. So a lot of learning has taken place. Now of course, we are in a position to realize that the what is the nameplate rating itself? What does it mean? When you say 22 kilowatt motor, is it the output or the input? So by now, I think everybody has become familiar about the rated kilowatt of the motor, that it's the output of the motor, not the input. So the motor itself, not much of potential. Then we go into the audit phase where we look into the energy cost for the company. So in this particular case, it is a simple automobile manufacturing company. Uh, this is the energy bill, and the LPG constitutes 25%, the electrical energy 75%. The typical audit approach, data analysis. So we collect data over a period of time and do the analysis, and this is a good reflection. So it's not only about the data, we need to convert it into information. So this is an information. We have gathered data and we have projected this as an information. It says 75% of our costs going towards the electrical energy. So the focus will be more on this. Even if you reduce 10% here, it's quite significant. And then all about the the tariff, what is the connected load, contract demand, and what is the energy consumption, and what is the actual maximum demand, what is the tariff structure. So all this is being collected. And where the energy is used, as we said in the energy audit questionnaire, where all energy is being used and how much energy is used. So the different sections of the plant, how much energy is. This is quite informative, and also today a lot of data is available. We don't need to struggle. We don't need to measure every motor in each shop and then come to this kind of a pie diagram. Today, many of the companies have this energy management systems where the data comes into the computer, and so this becomes an easy job. Uh, Going into the processes, so how we save energy in the end use. So here is one case study of an annealing furnace, a pit type furnace. So this is the materials to be heat treated. These are the ones, and this will be lowered into this pit. The whole lid is closed with this burners, and then the heat treatment cycle begins. Now, if you analyze this, just it is closed and look at this alone, this furnace alone, what is the energy saving that you can think of? So there is some fuel which is being fired, LPG, and then you have the material inside. LPG is for the atmosphere, and then we have the electrical heating also around. So how do we save energy? Everything is closed, no heat loss as it apparently appears. The material is gone inside, and after maybe 9 hours, this will be opened and taken out. So as you look at it, where is the scope or potential for energy saving? So all that you will do is to measure the electric power for one cycle, and what is the weight of this material. So the electricity kWh per ton of this specific energy consumption will arrive at. But where is the energy saving? This is a question. So which means we need to look further into the process. So we are giving some heat to the electricity, and where is this heat going? Now you look at this basket. What is to be heat treated? So it is the material inside this. So the weight of the products, the material inside is 70 kgs. The weight of the basket itself, this is the basket as you can see, should be lowered into this. So this will be dumped into this, and this will be lowered into this. So this is 60 kgs. So almost equal weight for the products as well as the material which is handling it, the bucket. So if only this basket is not there, then directly 50% energy savings is possible because directly it is proportional to the mass. So here, what can be done is to reduce the weight of this. You see the 60 kgs. Then we have redesigned this basket in one case. So with lot of openings here, the openings also help to circulate the. You have the convective heat transfer taking place in a better way. So heat is uniformly distributed because of the openings, and the weight of this is only 28 kgs. So there is a 23% reduction in the electrical energy consumption by reducing the weight of this basket. So this is where we need to stretch ourselves as energy auditors. There is a need to stretch beyond the convention. So the typical a value engineering approach, as they call it, in the industrial engineering parlance. So keeping the weight minimum and also you reduce the material cost. So every time you make this, the huge amount of material you are using, and handling also becomes pretty difficult. So it's got multiple advantages. So there's one case where you go beyond the convention and then see how exactly the heat is getting utilized, where it is going, how much is going, and then you arrive at the possible solution. There's another case in the automotive industry making the engine valves. It's a continuous annealing furnace. Now, this furnace was about 1.5 tons per hour capacity. So it was moving along well. Then suddenly they decided one or two pieces of falling the side into the gap. So what they did was to provide a kind of a barrier here. So as you can see it clearly here. And this has taken away some width of the belt. So this side you can see this. So this barrier is to prevent the valves from coming and sliding into the gap here. So after this, the production rate has come down to 800 kgs. So now this is a typical a kind of firefighting solution that they've made, but they've compromised the efficiency and also the productivity. The production rate has come down, and the energy consumption, the specific energy consumption has gone up. So in this case, what has been done was to trim this to about 2 inches. So 4 inches, we reduce this to about 2 inches and both sides. So as a result, more material would be fed into the furnace, which reduce the specific energy consumption. But otherwise, typical conventional energy audit approach, if you see, okay, you measure the output, you measure the kilowatt hours, again kilowatt hour per ton, and look for any waste heat, something is there, recovery possibilities, the electric furnace. So that opportunity also does not exist. So when you are into that catch 22 situation where you find that there's no energy saving, obvious saving opportunities available, then you are forced to get deeper and deeper and observe. The key is observation. So the key is to ask questions why. So the question here was, can we load the furnace better? And if we want to load the furnace better, what is to be done? Why this has been done? Why there is a reduction in this belt width? Then that means there are a lot of talking that we need to do to the operator. Many times the manager level people may not be aware. They are into some other activity. But at the grassroots, you need to have a conversation with the workers, the operators, and look into the background why this was retrofitted. So they give you a lot of information. And then you look for improved solutions beyond this. This is a case of a paint shop, heavy equipment, machinery manufacturer. So these materials are coming. This is a paint booth, and there is an air supply fan on the top with all filters, and then it is supplied to this paint shop. Painting is done. So basically, there's a ventilation system for the paint shop. So there's a supply fan which is blowing air from the top, and then there's an exhaust which is removing the fumes, paint fumes, through these two fans here, 275 kilowatt fans. And then the heavy equipment keeps moving like this, the conveyor. Then there's a top port flush off fan. There's one more fan which blows off. A partial drying takes place here, and then it goes into the oven. So this is the system. Now here, okay, the plant says we already have a VFD for the fan. So fine, that option is over. So we are looking for putting up a VFD for the fan, but then the plant says already we have VFD in place. So nothing much can be done. And then the exhaust fans, of course, we measured and it was drawing 45 kilowatt, 75 kilowatt fan. So now what to do? Now you look at the production rate. The plant was designed for about 16 to 18 paintings per hour. That is the production rate. That is the production capacity for which the paint booth was designed. But today, the market being dull, just about 8 products are being produced per hour. So the intermittent time, one equipment to other equipment, is more now. But the fan, of course, they have this and they're operating at a lower speed, no doubt. But is it the optimum? So in many cases, this also is an opportunity. We have seen people saying, yeah, we have VFD for all the rotating equipment in the plant. So VFD is not a black box or a magic box which just by putting a VFD you're going to save energy. It's not like that. So how you tune the VFD, what will control the speed? Is there a feedback mechanism? What kind of feedback you're going to take it? So this is a question that remains unaddressed in many of the plants. As a result, we find that many of the equipment having VFD operated at 50 hertz. So when you question them why you want to operate a VFD at 50 hertz, then they say, please, it acts as a good starter. Starter, okay, but then VFD at full speed, 50 hertz, you're going to lose energy. The VFD itself will consume about 3 to 5% of the energy. So having a VFD and operating at 50 hertz doesn't make sense. This is a great opportunity. In many cases, we have asked them to bypass the VFD. Say compressors, there are 3 compressors, 2 are in operation. So they have provided VFD for all the compressors. So all the compressors are VFD. So one compressor operating at full load with VFD, one compressor at partial load with VFD. Doesn't make sense. If you have backup compressors, the base compressors will operate at full load. They don't need VFD. The one which is going to meet variable load needs a VFD. So there's a lot of thinking that can go in this direction. How the VFD is being used in the plant? Are they effectively being utilized? So this area is one gray area where, of course, we have been asking the plants to put up VFD. Now we are going to ask them to remove the VFD. So this is what happens when, without assessing the need, when you are going to use an equipment, it can result in more damage. So this fan, what is the optimum speed at which it should? Is this the optimum speed? That's a question. Then we operate this fan at different speeds. So say this fan 50 hertz, it is 67 kilowatt. At 45 hertz, it is 50 kilowatt. 40 hertz, 35. So it keeps on coming. At 30 hertz, we find that it is sufficient because the production, basically, this is required because the production is not the same as it was envisaged to be. 16 to 18 units per hour. Now it is only 8 units per hour. So correspondingly, the ventilation rate, the fume generation is less. So the ventilation rate can be reduced. And that ventilation rate can be reduced by this fine tuning the VFD to 30 hertz. And of course, for as a precaution, we have set it at 35 hertz. And this reduction resulted in about a huge saving. So almost they're operating at kilowatt. This is 50 kilowatt, and now they're operating at 17 kilowatt. So about 33 kilowatt we save just by fine tuning this speed. And we will not be able to do a designer job from the first principles, fundamentals, calculating the ventilation rate, the fume generation, possible in the scope that we have been defined to do. But trials can be done. So this is advantage that energy auditor has. Already the equipments are in place. Unlike a designer who does not know what is going to happen. The energy auditor is very clear. He is looking at the system, 16 units to 18 units. Ventilation rates are designed for that. Now it is only 8 units. So where do we cut corners? So reduce the frequency of this. And at the same time, as the input air reduces, the exhaust air also can be reduced. So here the fan has a damper. Further close the damper, keeping the draft inside the oven the same. So this energy also reduces. So this is another example where slightly getting deeper can result in huge savings in energy consumption. And at the same time, the pump, the circulating pump, the circulating pump here for absorbing the fumes. The air goes here, suppresses the fumes, gets into the water, and then exhausted through the exhaust fans. So there's a pump which is circulating water for absorption of the fumes. So as much as the fumes generation is less, the water circulation also can be reduced. Pump now operating at full flow. And after doing a study with the throttle valve existing, we find that the flow can be reduced by 50%. So they need to later on provide a VFD for this and reduce the speed. So this is another major saving that they've been able to get. And in the same shop, before the painting, there is a short blasting of the equipment components. So the components moves here one by one, little by little. So it goes here. Then there's a short blasting that is taking place. There's a short blasting machine. So during the short blasting, enormous amount of dust and fumes are generated, which is taken out by an exhaust fan here, situated outside the plant. So they have, due to the noise consideration, they have located the fan outside the plant, and there's a long duct which is carrying the dust and fumes. So if you look at this, one component goes, short blasting, dust generation, the fan throws out the dust to the back filter. Now, after this component to come out takes about 2 minutes. So there are some more operations are done, so slowly it comes out. Then the next component comes, there is a setting time, which is about 2 to 3 minutes. So if you analyze the cycle time of this process, in a total of, say, if you say 100% of the time, just about 30% of the time is the short blasting taking place. Remaining 70% is only adjustments, settings, and then taking out the component. But this fan here is continuously in operation. It's a huge fan. And so this component which are coming here, and once you short the short blasting start, the motors start, and the dust generation happens. So here the fan is continuously rotating. It's a 180 kilowatt fan, huge fan. So what the company has a soft starter for this fan. So what we have done is to interlock the short blasting motor with this fan. So only when the short blasting starts, this motor will start. So as a result, this fan operation came down by 50%. There is no need for this fan to operate continuously. There's one more manual blasting booth is there, which is also connected to this. So for that, there is a separate 5 kilowatt uh, a blower and a back filter that was planned, and then it is separated from this. So this is now operating with this interlock. So it's a very simple measure. But again, as an energy auditor, if you look only at the equipment, this blower, then you measure the power and say the loading percentage of the motors, this match, all that. Then maybe you measure the velocity. If you're more keen and passionate, you measure the velocities, and then you measure the efficiency of the blower. Then what? So efficiency is this is another thing that is happening around in energy audits. We measure all the efficiencies, blowers, pumps, and all that. So this blower efficiency, or you measure, we taught you everything there, power analyzer, inlet pressure, outlet pressure, everything measured, and you say it is 45% efficiency. So what the client is going to do? Do you think he is going to replace this with another blower which you're suggesting at 75%? Very least likely to happen. So rather than that, if you come back into the process, rather than doing all this activity around the blower, you come through this duct and see why this fan is required at all. From that why, you start the question. Then you find that where exactly the blower has to act when the dust is coming out. So these questions, when you address, then you find there's a 50% saving potential in this blower. So like this, there are plenty of examples. Like for example, in the tire industry, we have seen a very simple measure. So this is a tube manufacturing plant. So they make this tube for the rubber. This material sheets come out, and then the sheets are going into this warming mill, feeding mill, and then there's an extrusion that takes place. So the tubes are extruded to an extruder. A lot of heat is there. So there's a cooling required. Now you have this sprays. There's a cooling conveyor. Spray water sprays are there. So for this, there are these pumps which you will find here. Yeah, there is a 10 HP pump. So there was a 10 HP pump connected to this. It's a very simple process. So this water, whichever is falling down, will go back to the pump. Pump will pump it to the cooling tower, again bring it back. So one pump to carry it to the top of the cooling tower, another 10 HP pump to spray it into the nozzle. So two 10 HP pumps are in operation. Now, if you look at the spray, and then the delta T, if you see, the cooling tower is only 1 degree, which means the water flow is excessive. Too much of water is going into the process. As a result, delta T is very less. So now here, if you see, the width of this tube is only 3 inches, but the spray is almost 1 foot. So where the tube is not there, water sprays are happening. So you cut off some of these nozzles and restrict to only 3 inches. So about 60% of the flow can be controlled, reduced. So here there was a case where we replaced the 10 HP by a smaller pump, and one pump which directly sends it to the cooling tower, another pump which sends it to the nozzle. So this is another case where by attacking the process, look into the process. Pump is there, motor is supplying the electricity, pump is rotating, the pump is supplying the water. Where the water is going, it is coming here. How the water is being used? Is it being used efficiently? No. How to make it more efficient? Blank the nozzles. Then you save on the electrical energy. So by closing the nozzle here, we are saving the electrical energy consumed. So these are some of the examples where getting deeper and diving deeper can result in of energy savings. So is the case with the your fuel savings. How do you save fuel? Today you have no opportunity to save fuel in the boiler. The boilers are all very efficient. They are fluid bed boilers, or in the case of gas fired or oil fired, no questions. By default, they are quite efficient. In a fluid bed boiler, where is the scope for energy savings? ID fan has got a VFD, FD fan has got a VFD, PA fan, and then you have an oxygen controller which is maintaining the oxygen exactly at 4%. Hardly any scope in the boiler itself. But it is not the boiler alone. It's just like the motor, what we are discussing. Boiler is like a motor. It is supplying steam. So where the steam is going, so if you put 100 units of energy to the boiler, 80% comes out as steam. And steam distribution, there is little loss, 5% insulation, spread of insulation. Then 75% of the fuel's energy in the form of steam goes into the process. And 35% of that, let's say it's a dryer or something, goes along with the product in hot condition. So to make a balance, so 78% is the input, 35% is the output. And say steam condenses, 15% comes out as hot condensate, is recovered anyway. And there is a loss of 28%, say hot vapors, fumes, and all going through the process after heating. If you look at the relative efficiencies, generation efficiency, 80%. Distribution efficiency from the boiler to the process, 83% efficient. But utilization, 75 to 35, only about 47%. That means there is a huge potential to save energy in the utilization phase. If you save energy here, then you reduce the fuel consumption in the boiler. Because your steam consumption is reduced, your fuel consumption. So this should be the approach when you're looking to save fuel in the boiler. So it's not the boiler alone, but the end use. Yeah, this is a typical example we did for one of the chemical industries, kind of a process integration. So this is a solvent coming out from a process, impure butanol, coming out at 15 millicurie per hour, 30 degrees centigrade. We want to make this impure butanol into pure butanol, for which we will heat it to 124 degrees centigrade and then cool it. For heating it to 124, we are using steam. 130 kg per hour of steam is used. Temperature rises to 124. Then we have a cooling water supply system here. 37 kilowatt pump is operating. So from 124, we are cooling it to 40 degrees. It becomes pure butanol. All the vapors are evaporated, and then evaporation. After evaporation, there is this cooling. So 40 degrees. Pure butanol is obtained. Now, if you put this thing as it looks in the field, in the paper like this, then you find there is 30 degrees to 124, there is a heating. 124 to 40, there is a cooling. For this, we are using cooling water. Suppose we use this 124 degrees outlet from the evaporator to preheat the impure butanol here. So use this stream to preheat. That means, so here you have this 124-degree steam which is coming out of the evaporator. You put it back here through a preheater. So 124 here, you put it, you have one more heat exchanger, put it here, and then this pure butanol becomes 40 degrees, which is what is the product that you want. At the same time, the entering impure butanol gets heated up to 80 degrees centigrade. Further, little bit of steam is required. So 130 kg per hour here, we are going to use about 75 kg per hour. So you imagine the amount of steam that can be saved by this kind of a process integration. Not only the steam, but then the cooling water is completely eliminated. So there's 37 kilowatt savings here. So these are all the typical advantages that you have by extending the scope of the audit. And when you say energy analysis, as the Act defines energy audit as one of the components is energy analysis of the energy use. This exactly is what is the analysis of the energy use. At the end point where the steam is used, it's not about the fuel, it's not about the electricity, it's about the end use, where exactly this energy is required. So from there, if you see a critical examination, observation, and some brainstorming calculations, all this will result in huge savings in energy consumption. Right. So I think we have reached the end of the session, and at this point of time, I would like to stop, and I hope I've thrown some light on the aspects of energy audit. Any questions you have, you're free to ask.
Um, like that was really a very thought-provoking session. I mean, we have seen earlier auditors, doing this deep energy audits, but with now so many equipments in the markets with the label of energy efficient uh, um, products, like say there are fans, there are motors. So motors are also now IE5, which are energy efficient motors, and I mean, which is said to be deliver a very quick result. I mean, the moment you just change the equipment and get the results. And the earlier days, what you are talking about, I mean, that the energy audit was really deep. I mean, now I'm measuring that uh, for excess gas or so. All these things are very rare to see. The reason is that the earlier batches which have become energy auditors have been trained to do that, but a new generation of energy auditors which is coming up, so they are not trained to that level. I mean, that thinking, like where you said that the reducing the nozzle size or something. But so how do we inculcate that thinking into the new auditors, young energy auditors who are trying to establish themselves in this field? Because what is really energy audit, or I mean expected out of energy audit, rather than just changing the equipments or putting measuring uh, using meters, right? So how do we inculcate that culture in any organization which is into energy efficiency?
Is there a question to me?
Yeah, that's a question to you.
Yeah. So, no, as you said, today we find a lot of difference in dealing with the kind of people that we used to deal with maybe 20, 30 years back. Today, not many youngsters are, of course, keen on getting into the core sector. So we don't get the best of the talents in the industry right now. And even otherwise, there is a tendency for the people to, that there's now everything, the computer is there, and data has come into the computer. So people have a tendency to remain in their seats rather than going into the field and observing the equipment, which used to be the case in the earlier generation. So most of the time you'll find the engineers walking around in the field looking for problems, troubleshooting. But today it's all, a lot of paper work is there, but less of field investigations and getting to the roots of the problem. So I think most of this stems from a passion to deliver something beyond. So if the individual is capable and is interested and he's got a passion, so he will do it. But other than that, I feel that even the management has to look at it from that perspective, where we have seen engineers, making a lot of paperwork. Most of the time, for the engineers are spent, in spite of the kind of SAP and other process automation that they have on the computers, a lot of paperwork is there, and you find that people are working overtime only doing the paperwork. So that needs to be looked into by the management, and see that sufficient time is given for the engineers to go to the field and look into the operations.
Yeah. Yeah. Thank you very much. And now there are further questions from the audience. So I'll read out those
There is one
questions.
question from your question and
Yeah.
answers, a question to the faculty. What is your view for investments in digital energy management systems based on IoT? Which sectors will be better facilitated for monitoring, identification, reporting, analysis, alarms, forecasting, optimizing capability? Yeah, as we know, that IoT is only a tool. So IoT by itself cannot save energy. That what needs to be monitored, what is the critical parameter which needs to be monitored, what needs to be controlled. This has to be first decided before you launch an IoT. Because it should not result in collecting a maze of data and then you don't know what to do with the data. So what is the critical data that needs to be controlled? So that requires a lot of inputs from the field engineers, the field managers. So I think this is what we need to look into. And the other thing is, as you rightly said, uh, science and techniques of energy audits in India, well known. But yeah, we have this question.
Should I read it out?
Yeah, but an energy auditor does not save energy per se, but identifies where and how energy is used. To establish that energy is actually saved requires, as you rightly mentioned, a measurement and verification system. So the transition from a EA system to MNV system has been rather slow in industry. What is that? Why is that so? So how to check whether we have saved energy or not? Measurement and verification. Very difficult. Actually, there are so many parameters which are involved, and to have a perfect measurement and verification system is a big challenge. So that is one of the reasons why not many ESCOs have been able to take off. The simplest thing is, you need to go by equipment and equipment by equipment. Suppose if you're making an impeller change for a pump, the pump alone should be critically monitored rather than the process as a whole. So you put a meter for the pump, a flow meter if possible, a power meter, and then before and after you go into it, you collect the data, then there is a possibility of success. But otherwise, organization wide, if you're going to make changes and look for measurement and verification, it's a huge challenge. And I think it's next to impossible because of the so many factors that are involved in the energy consumption pattern. So the next question is, my views on getting a better quality of young energy auditors is that AE needs to do road shows in universities. Okay, with people like Narayanan, and of course showcase the opportunities. Yeah, I think we are all doing our best. So in whatever way possible, whenever somebody calls for this kind of lectures, we are always there to
So
assist them.
that's
Yeah. So uh, we are here, but yeah, the always people are looking at what kind of opportunities are available and what is the ultimately it boils down to what kind of perks that we get. So when you if you see again the last 20, 30 years, the IT field has drawn away many potential talents. So we are already suffering from that. But all said and done, with the introduction of this examination system from the BE, it has certainly been a big turnaround. There has been a huge jump in the quality of people who are there manning the industries, who have gone through this examination system. Not necessarily that they should have passed the exam, but even going through this process of reading these
books.
books, I think has helped them a lot in going ahead. So I think in the future, this will be possibly addressed. More and more people will be drawn into this profession. So we hope so.
Yeah. So at CTech, like we ensure that whosoever is joining, so in the first month he goes through all these books and then he goes to the field. I mean, so we also have our own set of examination
Yeah.
wherein we evaluate them and based on these books. So really, these books are very helpful for
Yeah.
energy auditors and companies like us.
Yeah, correct. And more of the success stories have to be spread, uh, because these are all some challenging work. The energy auditor, as he comes out with some energy saving solutions, it's definitely challenging work because already the designer has come out with some design, and then there are operating people who are doing a good job. And beyond that, if you're going to do something to improve the uh, energy efficiency of a system or a process or an equipment, then it gives you a great satisfaction. So there is a change that we see is happening now, with more and more people getting attracted towards this energy audits. So all said, compared to other fields, this is still a budding area. So I think now you will find in another few years more and more people getting attracted towards this.
So,
Yeah. Any other
yeah,
questions?
yeah. Any other questions from the audience? So, thank you, Dr. Nagesh Kumar. That was really, really wonderful session, and hope younger energy auditors learn from it and make changes, necessary changes in the way of working, and all the even the energy auditing firms take a note of this and improve the quality of audits and put to use the best of the knowledge that is available in the field. Yeah. So, thank you everyone for attending this session, and we really love to see more and more people are attending this sessions regularly, and we will keep on going throughout the year, and so be stay connected to us through emails, through on LinkedIn, and also let us have your feedback and suggestions if you have for the sessions or any other activities that AEE can take up. So thank you.
Okay. Thank
And
you very much for all the participants and the madam for organizing this webinar. So thank you very much, and see you again in some other
it's a
forum. Thank you very much.
Yeah. So somebody has asked you whether the presentation will be shared. So all our recordings of the sessions are on available on our LinkedIn page. That is AEE Western India chapter. You search on LinkedIn and you will get all the recordings there. So not presentation, but the recordings are available. So that is better. Yeah. Thank you.
Thank you
Thank
very
you.
much. Thank
Let's
you.
end the session.